That. Here's my velocity equation. What's my displacement equation if this is my velocity equation? That's it. Now, we're not going to do that necessarily. Instead, what we're going to do is exactly what the front row was advocating for earlier, which is this. They're saying, hey, raise the power, do the opposite, right, of the power rule. So if I have the velocity equation, I'm going to raise the power by 1. Whoops. To turn my velocity into the other one, I'm going to raise my power by 1. So t to the second. Divide by the power I get instead of multiplying by the power I had, divide by the power I get. Plus, now this is interesting, 20. What's the power of the t on this thing?
0.
T to the 0, right? So if I raise its power by 1, it becomes t to the first, 20 divided by 1. Which makes sense because we just drop these, right? When we take the derivative. And so I get negative 4.9 t squared plus 20t. Surprise, surprise. So what we do is we take the original equation, if we want to go the backwards, right, to go from a velocity equation or a rate equation to a displacement equation, or how much stuff we have equation, okay, we're going to raise the power by 1 and divide by the power again. Make sense? All right, cool. All right, so flip this over. You have some problems on the back. Go ahead and let's try the first one. Example, dy dx equals negative 2x cubed plus 6x. What would y be? So try that out, and I'll jump on that just right behind you. Give you about a minute to do that one. There we go. So I've got dy dx is equal to negative 2x cubed plus 6x. So I raise its power by 1, divide by the power I get. Plus, raise its power by 1, divide by the power I get. I'm going to clean that up to be negative 1/2 x to the 4th plus 3x squared. Agreed? Anybody not with me? Ain't this great? Let's do lots of these. All right, I got a few of you for you to do. Go ahead and do that problems. The notation on the bottom, you see the integral. What does that little sign mean? That sign means sum all the pieces, which means to take the integral. We are not going to take the integral. What are we going to do instead? We're going to take the antiderivatives. But the last time I'm going to mention that, I'm going to say take the integral, and we're going to just quietly take the antiderivative, not mention the fact that we're not really doing it. Fair enough? All right, blow through these.
So you put a negative when you're adding 1. You're going to have a...
Oops. All right, how you doing, Plum? Ready? Okay, so that's my velocity. I want to find the acceleration. You said take the derivative. I totally agree with you, because the derivative of velocity is going to be acceleration. And that would be what? Negative 9.8. Agreed? So then I ask you next question. I asked the traditional question, what's the acceleration at 2 seconds? So I put a 2 everywhere I see a t. And I get what? Negative 9.8. Well done. Okay, so those are my answers for those 2 questions. Agreed? Now, we're going to do something completely fake different. Ready, Flom? Let's say I give you that I throw up a rock, and the acceleration is negative 9.8. What's the velocity equation? Okay, so what would I do, Flom? I got to go back to the first equation, right? So I'm going to integrate, agreed? So we're going to raise the power by 1, divide by the power I get. Right? Let's do that. So I give you acceleration. So if I integrate acceleration, I'm going to get velocity. So sticking to the legitimate thing I have there, what do I get? What do I get from? What?
Oh, negative 9.8, sorry.
Negative 9.8 what?
T.
T. I love that. Negative 9.8 T. Now, Flo, please have this. Please be thinking full skier, because this is the moment where we teach you something that most calculus students can't figure out. It's beyond their pale. What did just happened? I took the derivative to get the acceleration. Then I took the antiderivative, and look what happened. Are these the same? We lost the 20. Why did we lose the 20? Let me explain it in a totally different scenario. Let me say the following. Let's say I asked you the following. I said, hey, the same Los Angeles question I've asked you all first semester. I say, hey, Flo, you're going to drive 50 miles per hour to Los Angeles. How long does it take to get there? You're going to drive at 50 miles per hour to Los Angeles. How long does it take to get there? Feel like you're missing something? What are you missing? Where you started. The rate cannot tell you how many cans are on the floor. The rate cannot tell you, the rate of acceleration can't tell you how fast you're going at the start of the problem. The rate cannot tell you how far you are from Los Angeles, so you can't use it to figure out how close you are. You can say how fast I'm getting there. You can do that, but you can't tell me where I started. We're going to call this idea initial conditions. We're going to call this idea initial conditions. We're going to say, what was your velocity at 0? Now, there's two ways to write this. There's the calculus way, and there's a more sensible way. I'm going to accept either. What do I mean by that? The calculus way would be to add plus some constant. Okay? So when I integrate, I expect you to write plus C. Does that make sense? Because, and we haven't done that so far. We did a whole worksheet where I let you slide on that. But when you go to integrate, you need to realize that the initial conditions, you don't have them. I might give them to you, but you don't have them. So you have a plus C there. The other way to write this would be this. You would write negative 9.8t plus, you look over here, what's this variable? What letter is this? V. So we're going to write V at time equals 0, which is said V naught, or initial velocity. These are both acceptable answers in AP calculus. The advantage of this is it's a reminder that what we're asking is, what is the initial speed? So if I said, oh, it was initially traveling at 20 meters per second, you'd throw that in there, right? Whereas this, you might miss that significance. It's not huge, but it is important. Okay? So now we're going to drift away from this a little bit. Okay? Let's actually flip this over. Let's go ahead and try the first problem in the back. Try the first problem in the back. It says number 63. Yes, I'm starting with 63. Makes me feel better. 63. It says dH dt is 1.5t plus 5. Agreed? So the H equation would be raise its power by 1, divide by the power I get, raise its power by 1, plus, and I'm going to use H naught. Its height at time equals 0. I have to put in there the initial condition. And so then I look over here and I'm going to go, aha! This is 0.75 t squared. I'm just going to clean it up this round. And then what's my initial height?
12 centimeters.
It's 12 centimeters tall at the very beginning of the problem.
Leave it like what in centimeters?
I think everything's in centimeters. I hope it is.
Okay.
If it's not, yes, it's h is height in centimeters, so it's already in centimeters. Now, if those didn't match, technically you have to switch it. That's not a trick we generally play on math students.
Yeah.
Yeah. So there's my height equation. And then it says they're sold. How tall are the trees when they are sold?
6 years later, I think.
There are 6 years later. Where does it say 6 years? Oh, 6 years.
6 years.
All right, good. So we got to put 6 in here. So h equals point. So h at 6 would be 0.75 6 squared plus 5 times 6 plus 12. That's at least 42. That would be 48. Is that 48? You guys all have calculators and things at least. 48? Okay, I'm going to go with 48. Hope that's right.
Wait, isn't it
It's not.
69.
So 6 squared, so I did 6 times 3/4. Oh, you're right, it's terrible. I did that wrong.
What are we smaller than 37?
Hold on.
Don't kill my population equation.
Hold on. So 36 divided by 4 is 9. 9 times 3 is 27. Thank you. So that'd be 69 centimeters. Golden? Got it? That's just about the hardest test problem you're going to see on the test. Right there. Although, you're going to disagree once you see the quiz. It's coming extraordinarily soon. I'm debating whether the quiz is next time.